Greetings, calculus students. Today we're taking a look at Riemann sums and definite integrals. Our objectives for today: the student will learn that subintervals need not be of equal width in order to calculate the area underneath a curve. The student will demonstrate the ability to apply Riemann sums and calculate provided bounded areas. And your essential question for the day is, can I calculate definite integrals? Okay, now a lot of this is going to be kind of thick, very wordy, very technical sounding. Just kind of bear with it as we try to get to kind of get toward the end of the lesson, so you can see that it's not all as bad as it sounds. We've recently been computing area under a curve using rectangles of equal width in order to keep the computations as simple as possible. Now what we're going to be looking at is that it is not necessary to have the subintervals have equal width at all. In fact, trying to have the subintervals have equal width has been causing some of the wide variation as far as the difference in between how far apart the upper bound and the lower bound are, because as the curve is steeper vertically, we have more and more of our rectangles extending outside of the area underneath the curve, or we have area underneath the curve that is not being covered simply because of the nature of the shape of the rectangles versus the nature of the shape of the curves. Okay, so let's take a look here at a typical type situation. Consider the area bounded by f of x equaling the square root of x and the x-axis, as well as x equals 0 and x equals 1. Okay, so getting a visual of this area that we are looking at. Okay, as you can see, and you should know well already, the parent square root function kind of emerges from the origin heading mostly vertical, but then changes direction radically within its first unit of the domain. So it starts off from mostly horizontal and becomes mostly vertical before it reaches x equals 1. Okay, our artificial boundaries are going to be the x-axis, the y-axis, and x equals 1. So, of course, that green area that just appeared there, that is our bounded area. Now, the problem has been, as I already alluded to, when we use rectangles of equal width, similar to the ones that are over on the right side of the bounded area, as you can see, as you approach toward the left side, you would get a whole lot of protrusion sticking out from underneath the curve, and as well as a whole lot of area underneath the curve that is not being covered. But if we allow the rectangles to become more narrow as they approach the steeper part of the curve, you can see the area that is either over covered or under covered becomes minimized just due to the nature of the skinnier rectangles. Okay, so the limit as n goes to infinity of the summation, as I goes from 1 to n, of the function evaluated at some point c in the ith subinterval times the change in x within that ith subinterval of the partition given by x sub I, x within the ith subinterval, equal to I squared over n squared. Now this is similar to what we've been working with as far as I over n, but by squaring them, it allows us to, as we progress further along within the domain, the bigger the x value, you get an exponential increase as far as how far we're traveling within the domain. So that's going to allow us to have these ever-changing sizes of intervals as we move through the bounded area. Okay, so c sub I was the right endpoint of each subinterval. Okay, and giving you a little bit of indication here in the graphic, there's your right endpoint of your first subinterval would be 1 squared over n squared. The second endpoint, 2 squared over n squared. The next endpoint, 3 squared over n squared, and so on throughout the entire thing. And of course, the problem did not say there were 5 subintervals. I just jammed some rectangles inside of this curve, and it just turned out there were 5, but it would be n number of rectangles. So I number of rectangles there, I squared over n squared would be the last right side of your the right side of your last subinterval. Now the length, or I should say the width technically, of the ith subinterval is given by delta x sub I. My program's malfunctioning here. There we go. I squared over n squared minus I minus 1 squared over n squared. Now that's not as confusing as it looks. Basically what that is looking at is the difference between two consecutive right endpoints of a subinterval, one that ends at I and one that ends at 1 smaller than I. So not a big deal there. It's just the difference between the two endpoints of two consecutive subintervals. And looking at the algebra there, of course, you got in the numerator on the right side, I minus 1 quantity squared is I squared minus 2I plus 1, but you got that minus sign in the middle, affecting some sign changes in the numerator. And then condensing, combining like terms, you've got 2I minus 1 over n squared. Okay, so that is going to become our delta term for this calculation. So our area is given by the limit as n goes to infinity of the summation of I equals 1 to n times of the function, evaluated at c within the ith subinterval times delta x of the ith subinterval. Okay, and plugging in with the particular function that we had, the parent square root function. So we have the square root of I squared over n squared, because again, our subintervals now have unequal width to them. Okay, so I squared over n squared gives us that progressive width as we move through the subintervals, and there is your delta x sub I, 2I minus 1 over n squared. Okay, simplifying a little bit and pulling the constants out, you have I over n cubed is constant, going to be unaffected by the summation. And the part that will be affected by the summation is, of course, all of the I terms, 2I squared minus 1. I'm sorry, minus I. Okay, well, 2 is a constant, so on that summation we can pull that one out, and I squared is n times n plus 1 times 2n plus 1 over 6. And from that we can subtract I, which is n times n plus 1 over 2. Now it looks like I've lost my 1 over n cubed here momentarily. Hopefully I find that here in a moment. Okay, simplifying the algebra, 4n cubed plus 3n squared minus n over 6n cubed. And as the limit of n goes to infinity, we lose the two trail terms in the numerator, and we're left with only the lead term in the numerator. Okay, so I did lose my 1 over n cubed momentarily, but did find it in the last line. It got redistributed, and you can see it in the denominator there, 6n cubed. So 2/3 should be our limit, or our area, underneath the curve within those bounds. Okay. Now this brings us to a definition of Riemann sum, and here's where things are going to get a little technical here for a moment. Don't freak out. Let me just explain my way through it, and then we'll see where it brings us to at the end of that discussion. Okay, let a function f be defined on a closed interval from a to b, and delta be a partition of the closed interval from a to b. Now, a partition is simply like a progressive breakdown of a particular interval. Okay, so as we're obviously dealing with these areas underneath curves that are being broken down into a certain number or an infinite number of subintervals, the collection of all of those subintervals is called the partition. Okay, so we're looking at a particular part of the partition, hypothetically speaking here. And the partition is basically defined as meeting this condition. It's given by A is equal to x naught, which is less than x sub 1, less than x sub 2, less than x sub 3, and so on, all the way up to x sub n, which is equal to b. So basically our finite interval from a to b is broken down into an infinite number of subintervals, and each one of those is a particular subinterval of the overall, which is called a partition. Delta x is the length of the ith subinterval. Now here's the same language that we've been seeing before. C sub I is any point that is within the ith subinterval, and the sum is represented by summation as I goes from 1 to n of the function evaluated at c sub I within the ith subinterval, and then multiplied by the change of x within the ith subinterval. This is called the Riemann sum of the function for the partition delta. Okay, again, that's kind of thick language, but we'll see where it's taking us here in just a moment. It's worth noting the sums that we have worked on in section 4.2 were called Riemann sums. So there's no reason to freak out over this language or the technicality of this thing. You've already been working Riemann sums. We just did not call them that. But those were general forms of the Riemann than the ones that we're going to be looking at now. The width of the largest subinterval of the partition delta is called the norm of the partition. Okay, so typically as you're moving through your curve, finding your area, when you get to the most horizontal part of the curve, that rectangle theoretically is going to have the largest width to it, and that guy is called the norm. He is denoted by some kind of funky absolute value bars looking guys. They're called, they look like double absolute value bars with the partition in the middle of them. Okay, so the norm is equal to the change of x, which is found by the difference between the two values, the two extreme values of that interval, b minus a, and then divided by n. Okay, for a general partition, the norm is related to how many subintervals of the interval from a to b as follows. Okay, so the difference between the endpoints of the subintervals from b to a divided by the norm is less than or equal to n. Now the number of subintervals in a partition approaches infinity as the norm of the partition approaches 0. So thinking about that ratio as the norm, which is in the denominator, approaches 0, then technically what that's doing is that's making the ratio between the numerator and the denominator larger and larger and larger. The numerator is staying still while the denominator is getting smaller, so the overall value of the ratio is getting larger and larger and larger, so that's causing the number of subintervals to increase rapidly. Okay, so definition of definite integrals. If the function is defined on a closed interval from a to b, and the limit of the norm goes to 0 of the summation as I goes from 1 to n of the function evaluated at c in the ith subinterval times the times delta x within the ith subinterval. If it exists, then the function is integrable, sorry, tough word to say there, on the closed interval from a to b, and the limit is denoted by this. And this is the notation that you are undoubtedly most familiar with through your travels on Calculus AB, and probably where you've been kind of wondering in your mind when we're going to actually get to it. Well, there it is. Okay, you've got the integral from a to b of f of x dx. Okay, we are on the doorstep of introducing the first fundamental theorem of calculus, so all of this kind of lead up to what we've been doing with the exhaustion method, and Riemann sums, and all of that is bringing us to the first fundamental theorem of calculus. So this discussion is nearing its completion. This is referred to as the definite integral of the function f, with a and b being the lower and the upper limits of the integral, respectively. Okay, so this is kind of turning the corner, getting to where we don't know where we no longer need to specify, a left boundary of x equals this and a right boundary of x equals that. Okay, it's about to be condensed into a singular notation that is going to calculate the area precisely. Okay, so for example, evaluate the definite integral of the integral from -2 to 1 of 2x dx. Now note, in order to integrate, the function must be continuous on the interval. Clearly, you cannot calculate an area if that area has a mathematical failure within it. So obviously, we need to be continuous within any integral, or any interval that we are trying to integrate, and clearly this function is linear, it is not vertical, so it is definitely continuous within the interval. Okay, for convenience, we're going to divide the interval into n equal subintervals, and we're just kind of making a little bit of a point here, so bear with me. Delta x sub I, okay, the change of x within the ith subinterval is equal to delta x. Delta x is equal to the difference between the right and the left endpoints divided by the number of subintervals. So in this particular case, our subintervals are from 1 to -2. Okay, so we have 3 units worth of width, obviously, to our integration. So 3 over n is our delta x sub I. By choosing c sub I, c within the ith subinterval, as a right endpoint of each subinterval, then c sub I is equal to a, okay, your endpoint, plus I times delta x. Okay, so our left-hand endpoint was -2, plus we have 3 units worth of width to our integration, of course, multiplied by I over n. Okay, so the definite integral is going to be given by the integral of -2 to 1 of 2x dx is equal to the limit as n goes to infinity of the summation as I goes from 1 to n times the function evaluated at c within the ith subinterval times delta x in the ith subinterval. Plugging in the information that we have, okay, we had a linear function of 2x. X is replaced by -2. There's our phase shift, plus 3 units worth of width times I over n. And then delta x is 3 units again worth of width over n subintervals. Okay, so as our sum moves from 1 to n, obviously the trail term in the binomial is, the numerator is increasing. Let's take a look at the summation. Cleaning up the algebra just a little bit, we have a 6 that was a constant in the numerator and an n that was a constant in the denominator we were able to factor out. Okay, now we have a good opportunity to split the binomial into a sum of summations. Okay, and the first summation, -2, is -2 times n. The second summation had another constant that could be factored out of it, couldn't be factored out of the first one, but there it is, 3 over n, and then that left I, and of course the summation as I goes from 1 to n of I is n times n plus 1 over 2. Okay. Cleaning up the algebra significantly, we have a limit as n goes to infinity of -12 plus 9 plus 9 over n. Clearly, as n goes to infinity, we're going to lose the 9 over n term, and we have -12 plus 9, and we have a result of -3. Okay, if f is continuous and non-negative on the interval from a to b. Let me backtrack here for just a second. Some of you may have been a little confused on that. Just occurred to me for the first time, y'all just saw a negative area. Okay, so what are we looking at here? How come we ended up calculating an area and ended up with a negative area? Well, if you look at the graph of this guy, what you're going to see is that a large chunk of the area in between -2 and +1 within that interval, a large chunk of it is underneath the x-axis. Okay, when you do integral calculations like this, values that are above the x-axis are going to result in positives, and values that are underneath the x-axis are going to result in negatives. If we were actually interested in calculating the precise area of that function, pardon me, couldn't think there for a second, calculate the area of that function, what we would have to do is we'd have to calculate it as two separate areas, the area that is above the x-axis and the area that is below the x-axis, look at only the absolute values of each, and then combine them by addition, and that would give us our total area above and below the curve. Okay, but we'll get into more of that here soon. Okay, back to this. If f is continuous and non-negative on the closed interval from a to b, then the area of the region bounded by the function, the x-axis, and the lines x equals a and x equals b is given by, as we've already seen, the definite integral from a to b of f of x dx. Okay, so evaluating the area of 1 to 3 of 4 dx. Okay, sketching the region can help, especially on these lower level, lower degree functions. You might discover a lot of geometry coming to help you out. Sketch the region. It might be a simple geometric shape. Okay, so looking at a little piece of a graph here, we're looking from 1 to 3 on the x-axis, and we're looking at the function y equals 4. Well, y equals 4 is a simple horizontal line bounded by 1 and 3, and the x-axis, we're looking at this guy. Okay, well, we don't need any fancy calculus in order to calculate the area of a rectangle. It's a rectangle that has dimensions of 4 by 2. Okay, so area is length times width. 4 by 2 is 8 units. Okay, so very simple demonstration of definite integrals and area there. Evaluate the area of the integral from 0 to 3 of x plus 2 dx. Okay, so there is your interval from 0 to 3. And as you can see, this one is not rectangular, but it is trapezoidal. Okay, we have two parallel sides of a quadrilateral. So we have bases of 2 units and 5 units. And height between those two bases is 3. Okay, well, we have a formula for that. Area equals 1/2 times the sum of the bases times the height. And simply plugging in the areas that are the values that we have an area of 10.5 units. Okay. Now, a couple of things we need to look at here. The definition that we just looked at of the definite integral definitely had our lower limit smaller than our upper limit. Now, there are some oddball situations that we might run into from time to time that might actually allow the upper and the lower limit to be in the same place, or possibly be backtracking through the domain, so the lower limit actually larger than the upper limit. Seems to be a contradiction in terms, but we'll see that here in a moment. Okay, so two special definite integrals that we have to be worried about. If a function is defined at x equals a, then what we have here is we have an integral basically being looked at in the exact same place in the domain twice. So the lower limit and the upper limit coincide, and common sense would tell you the answer to this. If the upper limit and the lower limit are at the same place, then what is the possible two-dimensional area between those two locations? Well, obviously there is no two-dimensional area between those two locations, so your area in this case is 0. Okay, if our function f is integrable on the closed interval from a to b, however, essentially what we would think of is our upper limit is actually in the lower limit's place, and the lower limit is actually in the upper limit's place, which would tend to send us backwards through the domain. Okay, well, there's not any real trick to this. Obviously, if we're going backwards through the domain, we've basically reversed the signs of what is happening there. Okay, so the integral would happen the same way that you would expect it to, only this time yielding the negative of whatever result that the integral produced. Okay, so for example, evaluate the integral from pi to pi of sine x dx. Well, once again, there is no difference in between pi and pi within the domain. The function is defined at this particular location. The limits are equal to each other, so the result of this integration is 0. There is no area in between those two positions. Evaluate from 3 to 0 of x plus 2 dx. Okay, so the rule tells us that we're going to have the negative of whatever the result of this calculation is. Well, we worked this calculation here just a moment ago. Okay, this time our answer is going to be negative, and we've got negative 10.5 as our area. Now, we did not look at those particular bounds on the previous problem that we looked at, but the problem is linear. It is non-changing as it moves through the domain, and the upper and lower bounds are still 3 units apart. So when it comes down to a linear function, it does not matter really where you look at it within the domain, as long as you're looking at the specified limits of the domain. Scratch what I just said. I'm medicated, my brain's not making any sense. Obviously, it makes a difference where you're looking at it as far as the upper and lower bounds. I got confused for a moment with a different example. Okay, this one was looking at between 0 and positive 3 in the domain. Okay, so we already had this area calculation at 10.5, but because the reversal of the nature of the upper and lower limits, we catch a different sign as a result of that. Okay, so don't pay any attention to the ramblings that I just said about not mattering which 3 units you look at underneath the or within the integral, because that's clearly incorrect. Okay, some basic properties of definite integrals, and then we are finished. If a function f is integrable on the closed intervals determined by a, b, and c, and this kind of goes hand in hand with what I was talking about here in a moment ago about the values of the area being negative underneath the x-axis. The integral from a to c of f of x dx can be broken down into as many subintervals as you would like. Okay, so you can look at it as an integral from a to b, and then add that to another integral from b to c. Okay, so that would cover the entire interval from a to c. So you can break it down into sums and differences as you see fit. If f and g are integrable on the closed interval and k is a constant, then the functions k times f, so a constant times our function, and or two functions, f and g, being added together, if those are integrable on the closed interval from a to b, then the integral from a to b of a constant times your function times dx is the same as pulling the constant forward, then working the integral, and then reapplying the constant. So that rule has been kind of a mainstay staple for us on just about every skill that we have used so far this year. And if you have an integral from a to b of two functions being added together, then you may break them down and treat them both as two definite integrals applied from the both from the lower sum to the upper sum from the original problem, and then combine the results of those two definite integrations at the conclusion of the problem. If your function is integrable and non-negative on your closed interval from a to b, okay, then you will end up with a positive area value, or possibly a 0 area value of the integral from a to b times f of x dx. We've already seen that it is possible to end up with a negative area coming out of the integral calculation, but that is only if the function gets underneath the x-axis, hence the need for the distinction there. It's got to be non-negative on your closed interval in order to get a positive area. And if f and g are integrable on the closed interval from a to b, and f of x is smaller than g of x for all x values within the closed interval, then your integration will follow suit as well. The integral from a to b of f of x dx will result in a smaller value or equal to than the function, or the integral from a to b of the function gx dx. Okay, and that makes perfect sense, because basically we're saying f of x is closer to the x-axis than g of x is. We would expect that area calculation to be less than the area calculation for the g of x function, which is further away within the same boundaries. Okay, the assignment was page 273, numbers 4, 5, 9, 10, and then 25 through 30. I'm not sure how far y'all got in class, how much time copying the notes down chewed up. Okay, the plan is this. At this point in time, I plan to come back to class tomorrow. We'll go back over your Part 1, Unit 4 test, get that back to you, and then I'll give you Friday in class to complete the assignment, hopefully, so you can turn it in, not have any assignment to worry about over the Thanksgiving break. So plan to work on that during class, and I will see you in class. Plan to work on that during class on Friday, and I will see you in class tomorrow with your graded tests, God willing.